Good morning, everybody. Sorry for the late start. Welcome to the research results presentation for Tack Coat Performance and Material Study. Bryan Wilson of TTI, Texas A&M Transportation Institute, will be presenting today. We ask that you hold all questions to the end of the presentation. If you're here in the room, there are handouts at the front if you'd like to take notes on that. And if you're joining us online, you can type your questions in the chat pod, and we'll hold those till the end of the session. And if you're joining online, please mute your phones so we do not hear the distractions. Thank you, and I'll turn that over to Bryan Wilson.
Okay, thank you everyone for coming out. In Texas tradition, howdy. I wanted to first acknowledge the other researchers on this team that are not present with us. The first is Arif Chowdhury and Sheng Hu from TTI. We do have Dr. Sang-Soo Kim with us from Ohio University, and he was also assisted by Munir Nazal and Ala Abbas from Akron. Let's see. Okay. So my presentation, I'll go over some introductory material about what the research is all about. I'll go over our methodology and the results, and then discuss our findings, and then how we may implement the findings and our recommendations. So first off, the importance of bonding for the life of the pavement. The life of an overlay is highly dependent on the bond quality, especially when you start looking at things like thin overlays. It can be very critical. Poor bonding is most easily manifest by slippage, cracking, or delamination, where you can obviously tell, hey, this thing isn't sticking to it. But perhaps one of the more prominent types of cracking that you may see due to poor bonding is something like fatigue cracking, or as we'll find in this study, perhaps even reflection cracking can be attributed to poor bonding. So just some very basic physics of what happens with a bond is it improves the load transfer and decreases the pavement deflection. As you can see in this very simple illustration, if you were to put two pieces of pavement, or as what may be easier to think of as two pieces of plywood, if they're not bonded, each of those layers will slip independently. Whereas if you were to bond it, even though the individual layers are the same strength, together bonded, you decrease the deflection. And as we can see when we do some modeling, it's even the stress concentrations at the bottom of that layer are decreased. This little graph here shows this is the stress. This is a 50% bonded scenario, and you get a higher stress concentration here. Whereas if this were perfectly bonded, this peak would be lower. It would be a less amount of stress in the upper layer. So overall, having a good tack coat is a critical part of achieving a good pavement layer bond. There are new technologies that are out that are attempting to help us improve the quality of our tack coats. The first one is trackless tack. The whole idea here is with traditional tack, it's sticky, which is good, but since you got to drive on it, a lot of the tack gets taken up off of the pavement. And so even though you put it down great, it doesn't stay down, and so it comes off. And on top of that, as any contractor will tell you, or anyone who's been on a job, this stuff is messy and sticky, and it just gets all over not just the equipment, but on your boots, and then you come home and you complain about tack coat messing up all your jeans and so forth. So trackless tack, it's a hard pen asphalt, which means that it has a higher melting point, and so when you spray it down hot, or even as an emulsion, it quickly hardens. And so at ambient temperatures, it's not too sticky, but as soon as you put asphalt on top of it, it reactivates the tack, and then it bonds the pavements. Another technology to improve tack coats is the use of spray pavers. In this case, what is normally the separate truck as a distributor is now implemented in the paver itself. These are two models, one from Caterpillar, one from Tack, and there's another from Vogel, and maybe there's some others that have entered on the market that I'm not aware of. But you can see here, you actually have a spray bar. In the Caterpillar version, you have bars in the front, and you have an additional bar in the back, right behind the wheels. In the Tack version, the spray bar is all right behind, or right in front of the screen. So the tack is being put down immediately before paving, and there's no chance of contamination from vehicles driving over it. And the whole theory is, if you do that, your tack is not contaminated, and so you'll get a better tack coat and a better bond. The goal of this project was to justify or reject these higher cost tack coat strategies. Obviously, there's the cost of the spray paver equipment itself that you need to consider, and then even trackless tack and some of these tacks that go into the spray paver cost a bit more than a traditional CSS1H or SS1H. And so once we decide, do you get a cost savings there over the long term, how can we modify the specification to promote a better practice? And we looked at two options, a performance-based spec and a method-based spec. If you look at the research objective, that is the individual steps that we want to accomplish throughout the project. First, we wanted to develop a layer bond test. Then we wanted to evaluate the bond performance and predict the long-term performance of different tack coat strategies. We assessed a minimum bond criteria through modeling, and then we wanted to evaluate the cost effectiveness. So maybe you get a better product, but if it's going to cost you 3 times as much, maybe it's not worth it. Real quickly, I'll just go over the bond test. There's been a lot of research from other agencies already on different bond test methods, one of them being the shear test shown here. There's also a tension test that's been looked at and a torque test. And we, through our literature review and our personal experience at TTI, we recommended the shear bond strength test. It reasonably represents the loading scenario in the field with perhaps braking or accelerating vehicles that would apply kind of a shearing motion onto the pavement. It's intuitive. It has very easy sample preparation and easy to test, and it's inexpensive. This piece is you can buy this for $5,000, and then you need a loading frame to test it, and you can use a Marshall loading frame for that. Just to explain exactly what you're seeing here, you take a core, and you're looking at the surface of the core here, so it's actually going this direction, and so your bond is vertical, and this has two halves. This is a sliding half here, and behind it is a fixed half, so it's kind of like a guillotine, and you'll break the sample vertically like that. So moving on to what was the field work we actually did. We looked at several variables. The first being surface type. We looked at a new HMA, bonding to new HMA, and bonding to a milled surface. We looked at 3 tack coat types, SS1H, trackless tack, and a rubberized tack, which was SS1H with a 3% SBR. The 2 application methods we used were supplying the tack with a distributor and with a spray paver. We looked at different tack rates, ranging from 0.04 gallons per square yard to 0.13. We looked at what happens if you actually drive on the tack to see if the trackless tack really held up and gave a significant bonding improvement or not. And then we looked at bond age. So we took cores right after testing, and then 8 months later we took a few more. All the testing took place here in Columbus, which is great for y'all. It wasn't so good for me because I'm in Texas, but that's all right. We made the trip up. We were on the ring road, 270, on the east side, between roughly US 40 and I-70. You can see there were several southbound and northbound lanes. We concentrated on these southbound lanes in the center, which we call the mainline lanes. We did some preliminary study and found that those lanes provided overall a uniform pavement to build on for the test sections, and also it was the most convenient for traffic control and so forth. The actual layout was something like this, where we took one technology. In this case, we started with the rubberized tack and the spray paper and placed 3 sections at different rates. Then we shifted over to the distributor with SS1H, placed some more rates there, and played around with the effective tracking. These were on the milled surface. On the new surface, we had again the spray paper with rubberized tack, again the SS1H, placed this time both with the spray paper and the distributor, and then we also had trackless tack. With this project, it was milling down, I think 3 or so inches, and then they placed an intermediate layer. So that was our milled test section, because it was right over the milled pavement, and on top of that they placed the a surface course. So that was the new surface test section. So construction occurred just about a year ago at the end of July. We first calibrated the equipment. So the distributor and the spray paper, we checked the rates to make sure we knew what we had. During the construction, we even measured the tack rate, as shown here by using ASTM D2995. And then in certain sections, we did a tracking application, as shown here on the left, where we took the distributor and told them to drive back and forth across the tack a couple times. Here's the 2 pieces of paving equipment. First, the spray paper sections were built, and after that, that's this top one here. And then later, we used just a conventional paper for the non-spray paper section. So after that, we sampled overall, given initially and long term, we sampled about 130 samples, and we took them back to the lab. We sent some of our samples to Ohio University, where they did some testing as well, and we tested at 2 inches per minute in the bond shear tester. And we looked at 2 parameters. One is bond strength, so what's the peak bond that you get, and also looked at bond energy, which is the area under that curve. That's nice. Okay, so looking at the results, let me go ahead here. So overall, these are the graph for bond strength and bond energy. Just looking at all the data altogether, we ranged from 80 to 420 psi with an average strength of 210. And for bond energy, that goes from 0.4 to 6 foot-pounds per inch squared with an average bond energy of 2.2. And I've drawn in some lines for guidance for what we might consider a high and a low bond. As you can see, by a large majority, the data is a good bond on this project, with a few samples that actually got into the low range, but generally everything's at least moderate, if not higher. When we look at just a quick breakdown of the statistics, before the statistics, we analyzed the data into different groups. We wanted to first look at testing agency, So how does TTI's lab compare to Ohio University's? We wanted to look at the effect of the tack type and the application method. We wanted to look at the tack rate. We did analysis for surface type. We did analysis for tracking and analysis for the age of the bond. And our sample sizes, the smallest one we have is 40. So we're in that comfortable statistical range. And here are how the results came out. Basically, what I want to show you is, was it statistically significant? No, yes, no, 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 yes. So testing agency, was it statistically significant? No, meaning the sample that TTI tested and the sample that OU tested came out statistically the same. And I don't have the results themselves. Well, they're on the slide, but they're hidden if you want to see them. I can show them to you at the end. But no, testing agency, we both got the same result. The difference between tack type and application method, yes, very statistically significant. Changing the tack rate. There were some trends here and there, but overall, no, it was not statistically significant. So doing a low rate and a high rate, in the study we did, we couldn't definitively say that one was better than the other. Looking at the difference between a milled surface and the new HMA surface, we didn't see any difference in the bond. That being said, we have had other experience at TTI where we did see a difference, where milled sections, as long as they're nice and clean, generally give you a better bond, but you can also have a very dirty milled surface, and then you get a very poor bond. In this case, both sections have good bonds. Tracking did not prove to be statistically significant. That being said, when the tires were tracking back and forth, that distributor wasn't traveling off-site, bringing dust and dirt onto the project. So while it did pick up some tack, it didn't affect the bond. But if you were to have a truck that had a bunch of mud or dirt caked on its tires, that would probably affect the bond. And then we did find that the bond age was statistically significant. So this graph will show you the results of the tack type, application method, and also the age. So you have on the far left, this is your trackless tack, places the distributor. That had the highest bond. The bond strength was above 300 psi. And even after 8 months, here it's still above 300 psi, statistically the same. The next best performer was SS1H, places the distributor, had bond strength above 250. Over time, it increased a bit, although not statistically significant. After that, the no tack had also a very good bond, which may seem surprising, but asphalt by itself is sticky, and you're laying asphalt on something, and so as long as that surface is clean enough, it will stick. And then after that, the two spray paper sections had the lowest bond strength. What you should note, though, is even though they started out with kind of a moderate bond, after 8 months, these two sections increased the most, going almost doubling in some cases, going from 100 psi to 200 psi, well into that high bond range. What happens there is the spray paper puts the tack down immediately, which then immediately gets covered up by HMA, and some of that moisture is still trapped under there. But with time, that moisture does evaporate, it does get out of the pavement, and your bonds increase. If you shift over to look at bond energy, you'll see the trend is largely the same, just maybe a little more pronounced in showing the trackless a little higher, and no tack is dropping a little bit, but still that the ordering of these is the same. And again, you see this bond strength or bond energy doubling on the spray paper section. So we can talk about bond all we want, but if we don't translate that into actual performance, who cares, right? You can have the best bond strength in the world, but if that actually cracks sooner than these, then who cares how high it is? You know, we may want something else. So we're going to shift gears into looking at the long-term life cycle cost analysis. The first step was to develop a performance prediction model, taking the input parameters, putting it into a model, and then getting an output of how long is this thing going to last. And then with those results, we can then estimate a long life cycle cost. We had many inputs that went into this, such as layer thicknesses, layer stiffness, traffic, climate, and so forth. The one thing we were adding that was unique was this bond parameter. So what we did is we took our bond strengths from the lab, we converted those to a shear modulus, which is an interface property here, and then we could run the model. And to be totally honest, the one, if I can get my mouse to work, the biggest unknown that we had into this model was how to do this conversion from bond strength to the shear index. We did a lot of testing with just the shear index itself, which we feel very good about, but how do you actually take a bond strength of 400 psi and convert it into this other metric? We still got to do some more work on that. But what we did is we based it off of some results in the literature, our own personal experience, and I can describe that in further detail later on if you'd like. Or it's right here. I'll talk about it now. So like I said, how do we do this transformation? We looked at things like, we try to get the extreme. What's the very lowest bond strength that we've ever observed? And we put that as our lowest value in the shear index, which is a 2. And everything below that we could never core. And at the high end, we said, what's the highest strength we've ever observed? And in the middle, what's the kind of strength that we've seen that straddles this good performance, poor performance? So we looked at NCAT and where they observed some cores that were near delaminated areas, and we put that in the moderate range. As I said, we ran the model with different parameters with the layers. We looked at 3 different performance factors, the first being reflection cracking. If you were to look at the aerial views of that highway, that's a predominant distress out there because it's built over concrete. So that will be the first thing we feel that you'll see coming up are those reflection cracks. So how does the bond affect that? The next 2 things we looked at were rutting and the fatigue cracking. What we found, just varying that bond modulus, we found some interesting things. Well, first of all, we found that as you play around with your assumptions, the final result vary quite a bit. But if you assume that the same bond condition of that milled interface and the intermediate interface are the same, then if they're both at a full slip condition, you get the worst performance. This is with reflection cracking. And you'll see about 90% of your cracks come up in less than 50 months. So about 2 years, okay? So that's bad. If you have a full bond condition, you get something better, okay? But what if you were kind of in between? You had sort of a, not a super strong bond, but something more moderate. You actually, based on this model and the specific conditions we had out there, you actually get better performance. And what's happening is that bond, if it's a perfect bond, any movement down below due to thermal action is going to come straight up into your overlay, because any movement here has a perfect bond to the overlay on top, and it's actually going to create more stress at the bottom, and it'll crack faster. If you have a little bit of give there, just a little bit of allowance for sliding, you actually get a better performance. And let me reiterate, that's not the case for every pavement you're ever going to build. A lot of it depends on the layer thicknesses, the layer properties, and so forth. So, but in this certain scenario, that kind of half bond scenario is actually better. When you look at rutting, if you have a full perfect bond, you get the least rutting. And if you have a full slip condition, you get the worst rutting, and half bond is in between. So this is, here we're looking at half or a quarter inch over, this is about 15 years. So not an issue. On this project, if you have rutting, either we messed up or there's something else going on out there, because it should not be a problem. If you look at fatigue cracking, we found that a no bond gives you the worst life. So this is that's 10 years, so 9, 8, 7, 6, about 5.5 years of when the fatigue cracking will be predominant. Whereas if you have a perfect bond, you have over 100 years of life. Obviously, that's not true. Something else is going to fail before then. But as far as fatigue cracking, it shouldn't be an issue according to our model. So now let's look at the actual performance data from our test sections. Based on our results, if you were to look at reflection cracking on the new HMA section, even though the trackless tack had much higher bond strength than the spray paver sections, they were actually all very good. If you remember, they were all in that high range. We're using the 8-month data, so not the data right after construction, but after we've given it a little bit of time to cure and break. All the sections predicted the same pavement performance. In this case, we have the reflection cracking coming through by like 90% up here after about 7 years. So interestingly, not much difference, because all the bond strengths were good, and having an even better bond didn't contribute that much to actual performance. When you look at the milled HMA sections, it's a little bit different. Still very similar, but in this case, the spray paver sections actually had a little bit better performance. You're looking at about 9 to 10 years of life for the spray paver, where the other sections were at 8 years. Still not a huge difference, though. So let's convert that to cost. What we did was we took the cost of the materials, we took the cost of any kind of maintenance and rehab you'd have to do over 15 years, and added that all up. So the cost per lane mile for the sections here was just over $200,000. And I mean, that's a little higher than what it takes to build it, because if you remember, our performance prediction models assumed that it would be fully cracked after, let's say, 9 years. So there would be some rehab to do to get to the full 15. But as you can see, not much difference among all these. The greatest difference we saw was about $3,000 difference. That's between the no, it's more than 3,000, but it's between the 205,000 and the 212. Overall, it's about less than 5% of the overall cost of the project. Looking at the milled sections, where there was a little more difference, the milled sections, we actually predicted a little longer life, so your cost actually goes down. But in this case, we're in about 165,000. Your trackless tack comes in at the most expensive, and the SS1H with the spray paver is the least expensive. A difference of about $10,000. Again, you're looking at about 5% of the overall cost. And when you were looking at margins that slim, then you start to ask yourself, well, are the models, like, are they perfectly correct? Did we assume the costs were perfectly correct? And obviously no, right? There's some slop in there. And so in the end, the difference here kind of comes out in the wash. If we had seen, one of these to be, $100,000 less, well, then you could say there is a very good motive for pushing one technology over the other. In this case, we didn't really see that. So our key findings were that most of the bond measurements we made out in the field were acceptable, especially when you look at the 8-month data. Tack type, application method, and the bond age had a significant impact on performance. In this case, the trackless tack, the SS1H with the distributor, and no tack had the highest bond. Moderate to low bonds were achieved by SS1H and the rubberized with the spray paper initially, but after 8 months, the bond doubled for the spray paper section. We found that testing agency, so us and Ohio University, was not statistically significant. Tack rate, it was inconclusive. Statistically, not significant, but there may still be something there about tack rate to discover. Between the surface types and our testing, it was not significant. But again, we have seen other cases where a milled section does actually perform better than a regular, aged HMA, unless you don't clean it up, and then it's really bad. And then the effect of tracking was not statistically significant, which is interesting because the whole point of having trackless tack is to improve your tack code and improve the bond. But under the scenario for our testing, tracking on the tack actually did not affect it that bad. However, if you were to have trucks bringing a lot of dirt off-site, that would be a different scenario, and that could be really bad for your tack code. We found that having a better bond generally reduces reflection cracking and fatigue cracking, although there may be an optimal bond that's more preferred, maybe not 100% bond, but 70% or so. Better bonding also reduces rutting. Based on the 8-month data, all the test sections had near full bond conditions and similar long-term life. And if you look at the life cycle cost, we're looking at between $165,000 to $200,000 per lane mile. And the differences among the treatment types was between like $3,000 and $10,000, about 5% of the overall cost. And again, based on some assumptions we made and potential errors, that could just go out in the wash. We recommend using a shear bond strength test if you want to evaluate the bond of your cores or even lab molten samples. We wrote up 2 specifications. One is a method-based and one is a performance-based specification. So the differences are the method-based will prescribe to the contractor exactly what they need to do out in the field, where the performance-based spec says, you build it, we'll test it, and then we'll see if you did it right or wrong. So the method-based, the current spec is very good. So we just had some slight modifications, added some things to allow for spray pavers. We increased the recommended rates, or we allowed the recommended tack rates to be a little bit higher. And we thought it was best to prescribe the use of tack no matter what, even though we saw that no tack, in some cases, can actually perform well. Just putting a little tack on there gives you some assurance. In the performance-based spec, we moved the responsibility of selecting the tack rate to the contractor while still providing a minimum rate that they must have. And we added the bond strength test. The language there is the department will measure the bond strength of the new overlay to the existing surface on the first day of paving, and the core locations will be selected randomly. The average bond strength of 3 cores should be 70 psi or greater, with no single test result below 60 psi. If the contractor fails to meet this criteria, they must make changes to the tack coat, tack material type, surface prep procedures, and or application procedures. Paving will be suspended until the contractor constructs a test section meeting the criteria. I mean, this is what, as the researchers, we recommended. That's obviously up for discussion. But the idea is show us you have a good bond. Show that to us on day one. If you got the good bond, we'll leave you alone. Do your job. You know, we don't prescribe going out every single day. You're already taking enough cores to check densities. You don't need any more, especially if you're meeting bond the first day. Just leave us alone. Let us do our job. The final recommendation was a long-term data collection plan, which looks at bond testing initially and long-term. We've already done the initial and the 8-month bond test. We recommend going back after 6 years to see what's happened. Also doing some falling weight testing, spring and fall, about every 3 years. And most importantly, doing a distress survey. Do that annually for the first couple years, 5 years we recommend, to really see how fast are these reflection cracks coming to the surface. And then once you establish, about 5 years of annual, you can shift to a 2-year analysis. So it would be the easiest and most desirable outcome of this is, great, you test all this, what's best? Yes, we found SS1H with a spray paver is the most cost-effective, but the savings were small. So in the end, the department should consider allowing the contractor to choose the Tack material application methods and rates most convenient for their operations, considering they meet the minimum application rate and uniformity requirements. And just note that the initial bond from your spray paver can be much lower than from a distributor application. The bond will increase with time. This may be a concern, though, when paving in severe stopping and accelerating traffic conditions where you need a high bond performance on day one. So how might you implement this? This really isn't up to me. This is up to you all to discuss. But I just put some talking points here. You can implement the shear bond strength test. You can revise the Tack code specifications, as we discussed. You can put together a general best practices for Tack code construction webinar or similar, and you can implement the long-term data collection plan. Some activities that you may have are, the first thing is define what you want to implement and what you don't. Identify a leadership group in Ohio that can help with the implementation, to develop presentation materials, and of course the researchers at TTI and OU and Akron are happy to help with that. And then present those materials in key meetings and conferences and webinars, publish the results in journal articles. For the long-term data collection plan, find the team you want to do that, and schedule the activities, and then go do it. What are the benefits of doing all this? Ideally, you'll eliminate poor layer bonding and minimize the distresses that can occur. Now, this should save money to ODOT for premature maintenance and rehabilitation work, and generally we'll have a better understanding of the long-term performance of the different strategies. The risks of implementation, we want to make sure that there's a good tie-in between the bond performance, short-term and long-term, and the actual performance of the HMA. If you can't define that relationship, then you're kind of back at square one. So hopefully we can establish that. We want to resolve a difference in the initial and long-term bond performance. The question is, if you take a core on day one, what does that really mean? If it's going to increase, if it's going to double in strength, can you really trust the day one result? Maybe there's a way to get around that. Maybe you can age the sample in the lab or something like that. This is particularly important if you go and core, let's say a spray paver section, and it fails on day one. The contractor is going to be pretty mad because they'll come back and say, sure, it's bad now, but it's going to be just fine if you give me a week. So you got to resolve that. You may get pushback from the contractors for changing the specs and requiring an additional shear test. And you also don't want to add too much load onto the lab to perform this kind of testing. With that, that's the end of my formal presentation. And Kelly, we're opening up to questions at this point.
We have one question online, and in the shear bond test, how do you account for the stresses induced in the sample for the coring operation, from the coring operation?
Okay, so the question was, when you're coring, that procedure alone will add some kind of stress and could potentially damage the sample. So how do you account for that? As long as you're not adding so much stress to it that you're going beyond the peak strength, the sample should still be okay. That being said, core carefully. In our case, or in some cases that I've been on, we have to core the next day. If you core on day one, sometimes you can't get the core, but if you come back the next day, it's given it just enough time to set up and you can core it carefully. Other than that, just be careful.
Any questions in the room?
Yeah, I had a question on the no tack results. I thought that was kind of interesting, and I had a couple thoughts. One is, was the no tack result on the milled surface with the type 2 intermediate asphalt with no polymer versus the result for no tack with the surface mix that was polymerized, which is stickier? Which results are we looking at? Are we looking at both results for no tack, or are we looking at the surface?
So when we talk about no tack here, I could break it down. I could dig up the data and show, each individual section with no tack and so forth. Statistically, we couldn't separate them out. Statistically, they were the same. And so I presented them as kind of conglomerate. If I remember, though, on this test, the no tack samples, they did well. I mean, regardless of which technology or which surface we use. I have been on other projects where no tack is like you think, no stickiness, right? And it doesn't work very well. This particular project, it was okay.
So you can't generalize from this result that it would always be acceptable to use the no tack option.
Correct. Correct. And that's why in the specification we recommended always use some tack, because you never know. You don't want your project to be that project that doesn't work out, right?
Received another question. Is the type of emulsion important, such as cationic or anionic?
So on this one, the trackless tack was anionic, and then we used SS1H, which is also anionic. So we just did anionic on this project. There should be a difference, especially from the emulsion suppliers out there, that you need to marry your aggregate type to your emulsion charge. That was outside of the scope of this. Maybe someone else has some more insight into that here.
A question on coverage. You indicated that on the rate of application that there was no statistical difference with the results for the most part. And so was there a complete coverage with every application rate that you used, or were some of them so light that there was some gaps or streaking that was observed?
This section, everything was pretty well uniform. The lowest we went was 0.04 application rate, and even that looked good. Yeah, so no streaking on this job.
So you still obtain complete coverage?
Yes.
Okay.
Can you comment on potential performance on an existing non-milled surface?
An existing non-milled surface, that is the worst case scenario, and we had talked about that at the beginning of the project, like maybe we can find one of these sections to do the testing on. This ended up being the best project for us to work on But I have been on projects where, I don't know all the aggregates that you all use, but we have a lot of gravel down south in Texas, and trying to stick onto an aged gravel surface is not good. It doesn't work very well. But I have done some construction on, I'd lie if I told you what the aggregate was, but it was in an area that often uses granites or expanded lightweight aggregate. That bonded just fine. So a lot of it does depend on the existing age surface. You have a question here? Yeah.
I did. Slide 25 is a slide and it's titled Tack Type and Application Method. It would be on page 9 of the handout.
Okay.
That's the first slide on the top. And there you have the comparison of the bond strength for trackless put down by distributor, SS1H by distributor, no tack, rubber, and then SS1H by the spray paper. Did in all cases, with respect to the SS1H placed by the distributor, did in all cases was the tack coat set? And what I mean by that was the moisture completely evaporated out of the tack coat, so that you just had a black surface before you placed the gas.
As with the distributor section?
Yes, it was completely black. No water, water's all evaporated out.
Yeah, I believe so, right?
Yes,
it was a hot, it wasn't too hot by my standards in Texas, but it was pretty hot out there.
It was hot day too.
Yeah, and it was at least, and they had at least, most cases, 30 minutes before any paving took place, I think, yeah.
Another question is this on slide 23, page 8, middle slide, bond result. You said that all of the tack materials and methodologies used resulted in good bond results. Well, whoever set the bond results, I mean, whoever set what's good and what's bad, where did that come from?
Right. Yeah, so that came from experience. It came from taking cores, testing coring and saying, I can't core this because it keeps breaking. So that's our low bond. And then taking it next to it and saying, oh, good, I got this core, I tested it. Oh, actually it's about 50 PSI or 60 PSI. That's bad, right? And then for the good bond, we would test in between the layers and, we got whatever we got. Then sometimes we'd test within the mix itself and we would get, somewhere upward 300 or 400 PSI. It's kind of, we know that's good. And just, at this point, a lot of it's empirical.
I guess I'm wondering, is this from data that was pulled off of this research job, or is this previous research?
It's kind of a whole conglomerate of previous research and this research, and looking at it from an empirical standpoint and saying what looks like a good bond and a bad bond. Again, that comes down to the question of that in our models, trying to transform bond strength data to that model parameter. There's more work that needs to be done there, and that's a lot of heavy modeling and theory and so forth.
Well, it's in that bond strength that depends upon your facility that you're, if you're running heavy trucks, there's a different need there as far as bond strength, or it could be slow moving type of stopping where you may need a higher bond strength. So something might be inadequate that may look appear to be adequate.
That's a good point. So just because you're high for a low volume road, it's perfect for a low volume road, but maybe not for a intersection with trucks at it.
Go ahead. What was the highest rate you put the tack down this test?
The highest that we reached, about 400 PSI.
What was the highest tack rate?
Oh, tack rate, excuse me. We did, this is residual, 0.11 residual, which was, it was 0.13. Say what? Yeah, 0.16?
Yeah, it's only page 5 here, made out something, so it's all there.
I think it's 0.13. Does it say 0.16? No. What's that? Keep going up. Here I got 0.13. Before that? Well.
Yeah, it's on the presentation.
Oh, okay. Huh. Oh, I see. I see where it's here. I'll check with you. I can check. There may be a discrepancy in the presentation, but I'll let you know. That's about where we're at.
Is there any correlation of these results that you can take and apply it towards bonding to Portland cement concrete pavement base?
That would be outside of scope of what we did, but I guess, I mean, the question is, because bonding is it's both a parameter of what you're putting on top and what it's being put to, and a lot of that comes down to, you know, the charges of the charging of the bonding potential of each surface. So I don't know for concrete, like how much it wants to bond or not. But I know that is kind of an issue.
I noticed that the lowest result that you had, it looked like it was rubberized SS1HM. Maybe. It doesn't say what spec. You can say rubber on your.
Yeah. That's SS1H with 3% SBR.
And it had the lowest results in a lot of cases, it looked like. But that's what the current ODOT spec is for bonding to.
Okay. Do you have a comment? Great.
Well, Bryan, could you just discuss when you looked at the different test procedures, what's available, and then what the differences between some of the test procedures are as far as measuring bond strength? Maybe that might help.
Okay. Does that relate to this question here?
Yeah, I mean, you're measuring different things, and that's one of the things that keeps coming to mind when we discuss the no bond condition is using a shear test, and you know, some of the limitations of this test to discern things versus other tests.
Okay.
You went through that in the list version. I mean, that might be worth discussion.
Sure. Okay. So we're doing a shear test, which is we feel is the most representative of field conditions. With when you put on the brakes, you're applying an actual shear force to the pavement, whereas there's other tests like a tension test. So the shear test is going to combine both the effect of the tack and also the effect of the texture of the pavement. That's why a milled surface gives you a little more bond strength when tested in shear, whereas if you do it in tension, now the effect of the surface is sort of taken out of it. You'll get a different number, you'll get a different result. But then you're looking at closer to just the material property itself and not the effect of the whole system combined. So as that relates to your question, do you currently do a tension test for concrete or no? No. Okay.
Yeah, I told them that there's been successful performance with rubberized tack. I don't want anybody to take away that shouldn't use rubberized on concrete.
You know it works,
Yeah.
right? Yeah, if you know it works, then it works, right?
Well, yeah, I don't want anybody to, I guess, take away that from the result, because I think trying to marry two different things there. I use the research.
All right, thanks.
Another question, was driving allowed on the milled surface? And what determines if the surface is clean enough to create a good bond?
We did do tracking on the milled surface with the SS1H because that's typically the worst case scenario with dust and so forth. in this project, we just let the contractor do what they did, and they did a good job. It was clean. I don't recall if you put your hand down and wipe it around and seeing a bunch of dust coat your hand. I don't recall that being an issue in this job. We didn't take any specific measurements of cleanliness or anything like that.
My one is that we did require the paving train to be in the opposite lane of the transit.
That's true, yeah. When we placed the distributor sections, we kept everything but the paver in the adjacent lane so that they wouldn't, be driving on top of the tack, which you don't always get to do, right? Usually you don't. Right, because it takes twice as many lanes to pave that way.
Another question is, was the trackless tack undiluted?
I don't remember.
Yes.
Yes, undiluted? Okay.
All tack.
Yes.
How does the thickness play? Like, say you want to do like a thin layer, say it's just inch or less, so you're modeling. I don't think the shear test actually.
So you're asking if you're doing a thin lay for, like, how do you run the shear test on a thinner lift, or?
Tack rates or research in general, how would that play? Bonding is obviously more important to go. More back, higher tack rate, better.
So at least what we do in Texas, when they do a thin overlay, they specify, they often say you need to do a trackless tack, just because they know you get a better strength out of it. Whether that really means better performance is still for debate, as we saw here. And in Texas, maybe our freeways are bigger, because we often do put, at least the Austin area, they like to keep the paving train in the adjacent lane, like we did here. But again, that's not always feasible.
Any further questions?
Okay.
Okay.
Thank you.
A copy of the final report and this presentation will be available on the ODOT research website within a couple weeks, and that report will also include the method and performance specs that I had a chat question on. So please look for those things within a couple weeks, and if you have any other questions, you can email DOT research@dot.ohio.gov, or you can email Bryan Wilson directly. Thanks for attending today, and have a great day.